Okay. Good morning, everyone. I'm Yaoxuan from Department of Production Engineering at KTH. My research work mainly focuses on online monitoring processes based on multi-sensor technology and also AR algorithms. So today's in the next 20 minutes, I would like to share you with my recent research work with a topic which is called data augmentation-based surface roughness quality monitoring with machine learning models. Let me check if it is. Yes. Okay. First of all, today's presentation divided into 4 sections. First of all, is intelligent manufacturing system, machining systems, which I will give the definition of it and also a conceptual diagram of intelligent machining system and some the common applications of this system. Then we go for very specific application which build or establish on intelligence machining system, which is the surface quality monitoring and the production system, which is highly related to my current research work or even my PhD topic. And then I would like to dive more into details and explain more about how we combine machine learning algorithm with data augmentation method to build or establish the surface roughness prediction model during the machining processes. And later, I will wrap up my today's topic and come up with possible improvements or the future works. Okay, let's get started. So what's the intelligence machining? Intelligence machining is a process that's based on process monitoring and intelligence control technology, which is specifically designed to solve many uncertain problems in a process. The final goal of this system is to realize intelligence decision-making, monitoring, and control of the machining processes. This system establishes interaction with different systems, which include machine tools, sensors, controller network, big data, cloud-based data storage system. Through these systems, we can monitor and extract features from machine tools, cutting tools, workpiece quality. Workpiece quality here, I mean the surface roughness prediction. Just to visualize how it looks like. So this is a conceptual diagram of intelligent machining system, or we can call a smart machining system. It can divide into 2 parts. The first part is the cyber environment. The next part is a physical environment. For the physical environment, is our on our the shop floor. There are many different CNC machines and keep running, and we capture the different kinds of data during the machining processes. Those kind of the data or the signal submitted into the cyber environment. In a cyber environment, we store the big data, and then we figure out in which way we can do the data processing. Processes or the feature extracted data further submit to the machine learning algorithm, which we exactly pretty much rely on. And together, we build prediction models for the specific target. For sure, the cyber, there is the way that we use to connect cyber environment and also physical environment is integrated protocols. There are many ways that we can use in the integrated the protocols. Sorry for that one. I have to. Yes, here is just like the very special cases. It's like on the shop floor, individual and how individual CNC machine interact with the cyber environment. I will further explain this kind of like a loop or is kind of like procedures by using very specific cases. Here comes the very specific application based on intelligence machining system. It's a surface quality monitoring and prediction. So here, during the hard part turning processes, we capture 2 different signals by using microphone and also accelerometers, which is vibration sensors, signals, and also audible sound, the sensor signals. This is one part of input for the final prediction models. And the other group of input data is the surface roughness measurement. Because after each run, we need to measure the surface roughness along the workpiece from one area to another, which is the second group of the inputs of our prediction model. And the third one is the cutting parameters. The cutting parameter here is like the cutting speed, the feed, the depth of cut. So all this kind of three different groups of input data, which will be converted or transported into the prediction models as input data. And RA is kind of the surface roughness value as output of our prediction model. So RA is the output of prediction model. It's like exactly the predict the surface roughness value, but it is also can be input, which is converted into the sensor machine again. So a sensor machine again, based on predict the surface roughness value, perhaps can make a very, intelligent decision, which means the sensor machine can, based on the current or the predicted surface roughness feedback, and try to adjust the cutting parameters in order to keep the surface roughness generated during the machining processes in next moment, just keep within the same level, quality level, or to keep it within the satisfactory range. So this is kind of the closed loop, and we can monitor, and we can process, and finally, and we can control this kind of hard-turning processes. During this kind of cutting or machining processes, and we use there is a black wire which connected the piezoelectric accelerometers, which can capture or record the vibration signals, which represented in the blue line in the sub signal windows in 3 axes, and the microphone on the top turret, and we mounted on the top turret, which can capture and record the sound during the machining processes, which represented in the red line here. And for the green line is represent the motor current of the spindle in the sensor machine. But one thing I have to emphasize here, all the models or the results only based on the vibrate signals. But in my real cases, I use both of them. I use 3 of them, like the multi-sensor, so which means I use the sound, vibration, and also motor current to predict the model, and also to give the surface roughness. Some core technology and the challenge of smart machining system. The core technology can be, and we can get support from those kind of core technology, such as sensor integration, sensor network integration, integration of communication protocols, machine learning, deep learning algorithm, and also some advanced data acquisition technologies, or the method that we can capture or extract feature or very useful information from machine tools, processes, or the products. For sure, the system itself also has a few challenges. For example, the biggest one is big data accessibilities. Some of my local industrial partners mentioned it's never the big issue for them to capture the big data. But sometimes it's true, but sometimes it's not. It depends what kind of data. When we talk about unlabeled data, for them it's not a problem at all. But when we talk about the labeled data, it is still a problem for them. And even for some partners, they all have the big data, but they just randomly collect it, and they don't know how to store it and how to restructure it, and also without any specific purpose. That's really the big issue. So from us, we need the labeled data. In our lab, and the amount of data is very limited, and in the local industry, it is still very limited. So perhaps maybe data augmentation method could be the one solution to enlarge the amount of data for model training. And here is the general procedures on the surface roughness prediction model building. At first, we have to set up the experiment, and during experiment, we collect data. And later, when we have original data, we need to do the data processing and also signal processing. As I mentioned, considering very limited amount of data or original data that we can collect on the workshop or in our lab, so we have to manipulate or is kind of generated new data based on original data. So which means we need data or and the signal augmentation. And then when we get augmented and also original data, and we need to use the feature extraction method to extract useful information or the features from those the signals. Or the features here is can be like input for our model buildings. In the model buildings, compared with our researcher peers, they always build the model for the surface roughness prediction based on classification model, which means the output of their model can only tell you the level, the quality level of the workpiece. But here we use regression model, so which means our model output can exactly tell you the real value of the surface roughness, like 0.5, like 0.6, like RA value. So here is the differences that we are doing, and also the difference between us and also the other research work. And when we finish the model buildings, because we can give it a try to use the many different machine learning algorithm to build this model, and then we have to figure out the way and how we compare the performances from one model to another. So then we need to do performance comparison. So experiment setup. In the experiment, and we have to finish 2 measurements during and after machining processes. In the machining processes, we have to capture, so the vibration signal can automatically capture and record by the piezoelectric accelerometers in 3 axes here. And also after each cutting run or after the cutting process is finished, we have to measure the surface roughness through the profile meters. And for the cutting parameters here, during the experiment, we only change the cutting speed, and we keep the feed rate and depth of cut fixed. And all the experiments were finished or completed in a sweater machine in our lab, CNC machine in our lab. So when we get original vibration signals, how we can use like a data augmentation method. So here, I mean the data augmentation method is a Gaussian noise, masking noise, signal translation, time shifting, amplitude shifting, to generate it or manipulate the new data based on original vibration signal data. So here is one original vibration data, and through this kind of augmentation method, we can generate totally 5 new vibration signals. When we have original vibration signal and also augmented signals, then we need to extract useful information from those signals. So which means we need support from statistical features. So statistical feature like mean value, standard deviation of vibration signal can help us to extract useful information from those signals. And later, and when we have augmented the signal data and also original signal feature data, previously we only use original feature data divided into 2 groups. One for 2 groups of data, one for training algorithm, another one is for testing our algorithm. But here in our training data is composed of both original feature data and also augmented feature data. That is exactly the way and how we enlarge the amount of data for algorithm training. And hopefully by using the large amount of data, we can improve our performances of our prediction model. When we have enough of data, as I mentioned before, and then we have to choose which machine learning algorithm to build our prediction model. So in these cases, we selected 5 very classical machine learning algorithms. They are SVR, support vector regression, random forest, RF, gradient boosting regression, GBR, decision tree regression, DTR, and also extra tree is ET. So during the time limitation, today I don't want to dig into more details and give the further explain of each models. But among these 5 models, except support vector machine algorithm, The other 4 algorithms are totally like decision tree based or decision tree related, so which means constructed or built based on decision tree algorithm. Finally, when we build our surface roughness prediction model, and we need to use the model performance metric to estimate the performance of each model. So here I selected 4 indicators. They are like mean absolute. They're like MAPE, mean absolute percentage error, RMSE, root mean square error, MAE, mean absolute error, and also R square, which is coefficient of determination. So both of them try to correlate the surface roughness that we measured during the machining processes and predicted value of the surface roughness, which is the outcomes of our surface roughness prediction model. Here is the MAE results, mean absolutely error. In each machine learning algorithm, the deep blue bar represents MAE value provided by the model, which is only trained by using original data. And the other color represents mean absolute error provided by the model, which is trained by combination of original data and also augmented data. So from here, we can see almost all augmentation method can help us to help machine learning models to reduce the means of the value of the mean absolute error. The lower the value it is, the higher prediction accuracy model has. So compared with the deep blue bar and each of the other color bars has very the lower height, which means it has a very can reduce mean absolute error. But besides one case, it's like amplitude shifting in the SVR model and in decision tree regression model. These 2 are other exception. R square, coefficient of determination. R square value can help us to estimate the generalization of our prediction model. The higher value it is, the more robust of our prediction model it is. So again, we compared the different color of the bar with deep blue bar. So here give us values like by using augmented data, machine learning algorithm models can become more generalized or more robust. Here is another performance metric. It's called absolute percentage error, which can reflect the distribution, the real data distribution in the testing data. So the deep blue bar represents is kind of like the predicted results with absolute percent error less than 50%. So from the baseline and compared with the other augmentation method, this kind of blue bar height keep increasing, which means the number of the predicted results with absolute percentage error less than 50% keep increasing, which means the total accuracy of the predicted results keep increasing. Just to wrap up today's topic, time series data augmentation is an effective method on enlarging the amount of data. All data augmentation methods enable to improve the generalization of each algorithm. And in regard with prediction error reduction, Gaussian noise outperforms other augmentation methods in all algorithms. Actual trees and random forest bring the best outcomes than the other algorithm. When we talk about, then we can talk about a little bit about the future improvements. So the future improvements I mentioned before, by only use vibrant signal to predict surface roughness, maybe we need to take the other, like a sound signal and a motor current signal into consideration. By only use the time series augmentation method, perhaps we can use a spectrogram, or we call the generative AR-based augmentation method by using GAN's deep learning algorithm. In these cases, all the prediction models was built only based on very basic machine learning algorithm. Perhaps we can give it a try to use a more advanced deep learning-based algorithm to deploy prediction models. That's all for my today's talk, and thank you very much for listening.